In this video we're going to have a look at the way that we make confidence intervals for the mean. So the setup that we'll be considering is we have a sample of n objects. In this case we've got n beautifully drawn cats, I'm sure you'd agree. And we want to make inferences about the wider population from our sample. So in this case, let's consider a population that's the weight of cats across the UK. Of course it would be infeasible to catch all of them and to weigh them all, so instead we take a sample, here they are, of n such cats, and we can measure their weights, and then our challenge is how do we make inferences about the whole population and the population mean mu from the sample that we've got, which would have a sample mean of x bar. And of course different samples, if we chose different cats, that would give us different values of x bar. So clearly we can take the sample mean as a point estimate, but this doesn't say anything about its variability. It says nothing about our level of confidence in our estimates. So that's what we're really trying to do when we construct a confidence interval. And what a confidence interval is, let's say a 95% confidence interval, is an interval that's constructed in such a way that if we were to repeat the procedure that we conduct to make the interval many times for a large number of different samples, then 95% of those intervals, in the case of a 95% interval, would contain the true population mean mu. Okay, so let's try and figure out what the distribution is of the sample mean, because of course different samples will give us a different sample mean, so the sample mean itself has a distribution. So we're going to make the assumption that we have an independent random sample. So in particular we're going to let xi denote the mass of the ith cat, and we're going to assume that x1, x2, up to xn, in other words the weights of the cats, are an independent random sample from a normal distribution. So in other words, the weight of the ith cat, xi, is distributed normally with mean mu and some variance of sigma squared. Then what about x bar? Well, if we look at the sample mean x bar, then how do we get that? Well, we add up all of the weights of the cats, divide by how many there are. That's distributed as a normal distribution with mean mu and variance sigma squared over n. Okay? And this should match our intuition, because as n gets bigger, as we take larger samples, then the variance of x bar will get smaller. In other words, the bigger the sample we take, the more confidence we'll have, because x bar has a smaller variance. Okay, why is that? Let's just remind ourselves where that result came from. Well, it's because if we take expectations of x bar, then that's the same as this quantity in white here. Expectation of x bar, we can take the 1 over n outside, and we can split up the expectation of x1 plus x2 and so on up to xn as the expectation of x1 plus the expectation of x2 and so on up to the expectation of xn. That all comes because expectations are linear. So consequently we end up with 1 over n times this bracket. Well, what's this bracket? It's just n lots of e of x, because these are all distributed in the same way, and the expected value of any of these xi's we said was mu. So actually there's n lots of mu in this bracket here, so the expected value of x bar is mu. Okay, that's where this thing comes from here. Now, what about the variance of x bar? Well, the variance of x bar, I've just put the definition of x bar here. Well, remember, if we're taking a constant outside of the variance, we have to square it as we take it outside. So we've got 1 over n here. As we take that outside, that becomes 1 over n squared. And then, because these are independent, we can write the variance of a sum of random variables as the sum of the variances. Now, this means that inside this bracket here, we've got the variance of x1 plus the variance of x2 and so on, plus the variance of xn. Now, those variances are all sigma squared, each of them, and we've got n of them. So this bracket becomes n times sigma squared. We've got the 1 over n squared outside, and so if we simplify that, we get sigma squared over n. So that's why the variance of the sample mean is sigma squared over n. Right, so our challenge now is to figure out how to use that observation. So we now know what the distribution of x bar is. It's distributed normally with mean mu and variance sigma squared over n. How do we use that to make a confidence interval? Well, one of the difficulties is that normally the population variance is unknown. If I were to ask you what's the variance of a cat's weight, then you probably wouldn't be able to tell me, certainly not for certain. And so because the variance is unknown, we've got to estimate it from the sample data. Now, we've seen in the lectures that the way to do that in an unbiased fashion is to compute this thing called S squared. And this is just something that we calculate from the data. So a particular data set, we can do the number crunching and figure out what S squared is. That will be an unbiased estimator of sigma squared. Now, ordinarily, if we're going to try and make a confidence interval, we'd normalize the quantity that we have. So typically you'd subtract the mean and divide by the standard deviation. But because we've got this sigma squared over n and we're having to estimate sigma squared by using the data, by calculating S squared, then we do the same kind of thing, but we get a slightly different result. So we compute this thing that's normally called the T statistic, which is we take x bar, subtract off mu, and divide by our estimate of the standard deviation. So the estimate of the square root of this, because we're estimating sigma squared by S squared, we have S squared over n here, and so the square root of that will be the standard deviation S over root n. This is the thing that we call the estimated standard error of x bar. Okay. Now that thing, the T statistic, has a distribution of a T distribution, student's T distribution, on n-1 degrees of freedom. Right, now if we're trying to compute a confidence interval, let's call it a 100 times 1 minus 2 alpha % confidence interval, so alpha would be 0.025, for instance, in a 95% confidence interval. We're going to look for constants, let's call them plus or minus T alpha n minus 1, so that the probability of this distribution, so T n minus 1 here is a statistical distribution, the probability of that distribution being bigger than our constant should be alpha. And similarly, by symmetry, the probability of our distribution taking a value less than minus that value should also be alpha. So perhaps this diagram here of the PDF of a T distribution will give you a clearer picture of this. So we're trying to find these constants, so these kind of yellow points along the axis, so that the chance of exceeding T alpha n minus 1 is alpha, and the chance of being less than minus T alpha n minus 1 is also alpha, which leaves us, of course, with 1 minus 2 alpha in the middle, because this is a probability distribution, and so the area underneath the curve must be 1. So we've got 1 minus these two tails, 1 minus 2 alpha. So an equivalent way of writing this is to say, right, okay, we're looking for these constants plus or minus T alpha n minus 1, so that the probability of our T statistic, which is distributed in as T n minus 1, the probability of our T statistic being between these two values is 1 minus 2 alpha. And hopefully you can see from the picture that these two problems are equivalent. So how do we find these constants, these yellow constants, T alpha n minus 1? Well, fortunately that's really easy, because these are exactly the constants that the statistical tables give us. So if we pick an alpha, then go to the stats tables, they will give us these percentage points, T alpha n minus 1. So our only challenge now is to rearrange this inequality that we've ended up with in such a way to make mu the subjects, to make mu on its own. So let's have a quick look at how we'd go about doing that. Well, here's the inequality that we ended up with on the previous slide. If we now rearrange that slightly, let's do so by multiplying both sides by s over root n. Now, these are positive things, so s is positive, square root of n is positive, so actually by multiplying throughout the inequality by that, we don't have to worry about it being negative, which would flip the signs. So this is just a simple case of multiplying throughout by s over root n, and that gives us this expression here. And then to finally get mu on its own, what we'd do is we'd subtract x bar from both sides, and then that would give us minus mu in the middle, so then we'd multiply all of the inequality by minus 1, and that would then flip the signs, but then we could rearrange it and write it in a slightly different order, and it would give us the probability of x bar minus the number from the tables times the estimated standard error of x bar being less than mu being less than x bar plus the number from the tables times the estimated standard error, the probability of that is 1 minus 2 alpha. And so if we look at that interval, which is exactly this interval that we had here, that is a 100 times 1 minus 2 alpha % confidence interval for the population mean mu. Okay, finally, let's have a little think about what the interpretation of that is. Well, there will be a true population mean, mu. Okay, I've denoted that here with this dotted line. And were we to take many samples, we could calculate x bar. I've marked those with a cross for different samples. And we could calculate this confidence interval in the way that we've just done. So that would be an interval which I've labelled with these lines that go up to the bracket at the top and down to another bracket at the bottom. Okay. So, what's a 95% confidence interval? Well, it's that if we were to repeat this procedure many times with many different samples, then 95% of them would contain the population mean. Now, occasionally you'll have a kind of slightly freakish sample where it doesn't contain the population mean, but that would be a fairly rare event if it was a 95% confidence interval. That would only happen 1 in 20 times. So, the key point with the interpretation of these confidence intervals is that were you to construct them many times with many different samples, then 100 times 1 minus 2 alpha % of them would contain the true population mean mu.